You know that brilliant friend who takes like 20 minutes to explain the entire history of timepieces just to tell you it's 2 p.m.?
Oh, yeah. We all have that friend.
Right. Well, we are currently forcing our most advanced AI models to do exactly that, billions of times a day. And it is costing us, it's costing a massive fortune in computational power.
It really is.
So, welcome to the deep dive. Our mission today is exploring a brand new state-of-the-art research paper that tackles this exact bottleneck in how AI actually, thinks.
Yeah, the researchers introduce a framework called adaptive latent agentic reasoning, or ALR for short.
ALR, got it. And we are diving into how engineers are finally teaching AI to think quietly, efficiently, and, well, adaptively.
Exactly. Because the premise here targets something we are all actively chasing, right? We want to create AI agents that can independently browse the web, use software tools, and solve complex multi-step problems for you without needing constant hand-holding.
Which would be amazing.
It would. And we have the foundational technology, but right now, these agents are incredibly inefficient. They burn through processing power because they narrate every single micro decision they make.
Out loud, basically.
Yes. And if we look at the bigger picture, this research isn't merely about making your AI run a little faster or bringing API costs down. We are watching a fundamental transition in the interface of AI reasoning.
What do you mean by interface?
We are moving from AI that thinks in human-readable text to AI that thinks in pure, unadulterated computation.
Wow. Okay, that is a wild transition to wrap our heads right around. Let's start with what the researchers diagnose as this overthinking epidemic. Most of us just, we type a prompt and wait for the answer so we don't see the internal gears turning. How do current large reasoning models, or LRMs, actually operate under the hood?
So, to understand the bottleneck, you have to look at the current industry standard, which is explicit chain of thought reasoning.
Chain of thought. Okay.
Right. When you give an advanced model a complex prompt, before it gives you the final polished answer, it writes out a verbose block of text explaining its own logic to itself.
Oh, interesting.
Yeah, it will literally generate sentences like, first I need to calculate the total budget, then I will divide by the number of departments, therefore the answer is, and so on. It explicitly maps out its reasoning using discrete human words.
For a single, really difficult math problem, having the AI show its work seems beneficial, right? It acts like a cognitive safety net to prevent hallucinations.
For a one-off logic puzzle, yeah, that verbose text absolutely prevents mistakes. But the paper focuses on the agentic setting. And this is a totally different ballgame.
How so?
In an agentic setting, the AI isn't just answering a single trivia question in a vacuum. It's interacting with an environment over multiple turns.
Ah, okay.
Think about asking an AI to research a niche topic for you on the web. It has to formulate a search query, execute the search, read the results, realize it needs more specific information, formulate a second query, and so on.
And at every single one of those intermediate steps, the AI is doing that massive out loud monologue.
For every routine decision, it generates a full paragraph of text just to decide to click a next page button or type a new search term.
That sounds exhausting.
It is.
Yeah.
In industry, we call these reasoning tokens. In a multi-turn trajectory, these tokens pile up in the model's context window. Your system bogs down, response times drag, and the computational waste is just staggering.
Okay, the source material actually provides a brilliant visual example that perfectly illustrates this madness.
Oh, the El Capitan one.
Yeah, exactly. So the AI is given a multi-hop question. The prompt is, which college did the director of the film about El Capitan's free solo ascent attend?
Right, a classic multi-hop query, because you cannot just search that entire phrase and expect a direct answer.
Exactly. The agent has to break the problem into sequential steps. So, using the traditional explicit chain of thought model, turn one involves the AI writing out this massive internal diary entry. It generates, I need to first find out the name of the film about El Capitan's free solo ascent. That alone wastes 212 tokens just narrating its intent before it actually executes the simple search.
And then it reads the search result, realizes the movie is called Free Solo, and for turn two it writes, okay, now we need to find out who directed Free Solo.
Which is another 154 tokens burned.
Exactly. And then turn three, it discovers the director is Jimmy Chin and types out, Jimmy is one of the directors, let me search for his college. 113 more tokens.
So by the time it finally spits out the answer, which is Carleton College, the AI has burned through 543 tokens of pure self-narration.
543 tokens just to organize its own basic search process.
It's like asking someone to make you a peanut butter sandwich, and instead of just walking into the kitchen and doing it, they narrate every micro movement out loud.
That is a perfect analogy.
You're like, I must now extend my right arm 45 degrees to grasp the knife handle with exactly 2 pounds of pressure. Okay, now we must navigate our physical form to the pantry jar.
Right, right.
It is exhausting, and it's completely unnecessary for a task they already know how to do.
The inefficiency is glaring, and the AI industry is acutely aware of it. Which kind of leads us to how developers have historically tried to solve this bottleneck.
Well, the intuitive fix here seems pretty straightforward, right? If the AI is writing too much text, you put it on a word count diet. You just force it to summarize.
And that has been the dominant approach. The researchers point out several current industry solutions that attempt exactly that. You'll see methods with names like Think Prune, O1 Pruner, and Shorter Better.
Catchy names.
Yeah, they all operate on the foundational principle of textual compression.
Meaning they're actively pruning the redundant thinking steps out of the AI's internal scratchpad.
Exactly. They enforce strict length budgets, or they use reinforcement learning algorithms to reward the AI for arriving at the correct answer using fewer words. They are trying to train the model to be concise.
Okay, I have to pause here because that feels structurally flawed to me.
How so?
Well, if we force the AI to compress its thoughts into a tighter text budget, doesn't that inherently limit how smart it can be on that specific turn?
That is exactly the issue.
Right. Because if the model's only mechanism for processing a problem is generating language, and we suddenly chop its allowed word count by 80%, aren't we just artificially capping its cognitive depth?
Yes.
It feels like telling a brilliant mathematician they have to prove a complex theorem, but they're only allowed to use 3 lines of a tiny sticky note.
That observation cuts right to the heart of the paper's argument. Textual compression is ultimately a dead end.
Wow, really?
Yeah. The bottleneck is not the length of the text. The bottleneck is the textual chain of thought interface itself.
Oh.
When you demand that a routine step be translated into English, you're forcing the AI to use discrete vocabulary.
Okay.
It has to map its internal logic to specific words like therefore, search, or next. But a routine task like deciding to click a search link might not require textual logic at all,
Right, it just requires a quick internal mathematical computation.
bypassing the language translation entirely.
Okay, this brings us to the core innovation, right? The adaptive latent agentic reasoning, or ALRR.
Exactly. The researchers designed a dual-mode framework. The AI is given 2 distinct modes of thinking that it can dynamically switch between on a turn-by-turn basis.
Let's pull those 2 modes apart. How does the AI decide which brain to use?
Well, the first mode is latent mode, designed specifically for those routine, repetitive turns. Instead of generating English words, the AI uses latent reasoning.
Latent meaning hidden, right?
Exactly. It replaces the verbose text with a fixed-length sequence of continuous thoughts directly within the model's hidden state space.
Okay, continuous thoughts in a hidden state space versus discrete vocabulary. For those of us who aren't machine learning engineers, what is the practical difference between how the AI handles those 2 things?
When an AI generates a word to output to your screen, it's pulling from a discrete vocabulary. It has to commit to specific tokens: apple, car, calculate.
Right.
But before it ever selects a word, the AI processes information as complex mathematical vectors. Imagine vast, multidimensional arrays of numbers. This is the hidden state space.
Okay.
It is the AI's raw, internal computational environment. It's incredibly rich with nuance and probability.
So by forcing it to use words, we are forcing it to collapse all that rich, nuanced math into rigid text.
You nailed it. Latent reasoning allows the AI to stay entirely in that fluid mathematical space. It doesn't bother translating its intermediate logic into human-readable sentences. It just crunches the vectors.
And the paper notes that this latent mode uses a grand total of 4 tokens. 4. It brackets this a silent thought process with little tags, LAT and end LAT.
4 continuous vectors of pure thought. It is incredibly compact. So that's the first mode. The second mode is explicit mode.
Which is the text mode.
Right. This is the traditional verbose text we discussed earlier using think tags.
Yeah.
But ALR reserves this explicit mode only for hard turns that genuinely require deep, complex deliberation.
Okay. Let's run our El Capitan search example through this new ALR framework to see the dual mode brain in action.
Let's do it.
The AI receives your prompt. Under ALR, turn 1, finding the movie title, is a routine data retrieval step. So it engages latent mode, it outputs those 4 silent mathematical tokens, and instantly executes the search.
Yep.
Turn 2, reading the result and searching for the director, is also routine. Another 4 silent tokens.
Then, let's say on turn 3, the search results come back and they are messy. Maybe Jimmy Chin attended a few different institutions, or the text is ambiguous, and the AI needs to carefully reason through overlapping dates to isolate his undergraduate college.
Oh, so it hits a roadblock.
Exactly. The model recognizes this is no longer a routine click, it's a complex logic hurdle.
So the AI dynamically shifts gears. It escalates to explicit mode. It drops a think tag and writes out the logic in text to ensure accuracy.
Like, okay, the text shows he attended this school in 1996 for a certificate, but we need his primary undergrad degree.
Right. And even with that one explicit wordy turn, LRR completes the exact same multi-hop task using just 162 tokens, down from the original 543.
The efficiency gains are massive because the AI scales its effort to the specific difficulty of the microtask in front of it.
You know, think about how you drive to work. This mimics human cognition perfectly. It's the classic System 1 versus System 2 thinking.
Oh, absolutely.
System 1 is you driving your standard morning commute. You aren't consciously narrating your physical movements. You don't say out loud, now I will engage the turn signal and rotate the steering wheel 15 degrees.
Right, it's latent, silent muscle memory.
Exactly. But if you hit a massive detour and find yourself in an unfamiliar neighborhood, System 2 kicks in. You turn down the radio, you lean forward, and you actually start explicitly talking to yourself out loud about alternative routes and street signs.
That is a phenomenal way to visualize it. We rely on latent internal computation for the routine and explicit narrativized reasoning for the novel or complex. ALR provides AI with that exact same cognitive architecture.
Having a silent, latent mode sounds incredible in theory, but this raises a massive logistical hurdle. How on earth do you actually train an AI to do this?
It's tricky.
Because you can easily train an AI to write better text by showing it thousands of examples of good human writing. But you cannot supervise hidden states. They are just massive matrices of unreadable numbers.
This is where the engineering gets truly elegant. To train the silent latent mode, the researchers developed a method called action-anchored self-distillation, or AASD.
Action-anchored. Okay, let's break down how that works.
Imagine a boss asking an employee to generate a complex quarterly financial report. The boss doesn't care if the employee uses an Excel macro, a Python script, or mental math on a whiteboard, as long as the final report on their desk is perfectly accurate.
Right, just get it done.
AASD operates on that same principle. The researchers don't try to force the student AI's hidden mathematical vectors to match a teacher AI's English text. That's a structural mismatch. Instead, they anchor entirely on the final actions.
The actions being practical outputs, like calling a search tool, returning a specific value, or clicking a link.
Exactly. They take a massive, highly capable teacher model that uses long, explicit text to successfully solve a problem. They strip out all of that verbose textual reasoning from the training data and replace it with a blank latent block.
Okay, I'm followed.
Then they tell the smaller student model, we do not care what internal hidden state path you take inside this block. We just need you to produce the exact same next action the teacher did.
Wow, so the student model organically learns whatever internal mathematical shortcuts get it to the correct outcome without ever being forced to translate that journey into English.
It discovers its own optimal computational path. But that introduces a secondary, arguably harder problem.
Which is?
How does the AI learn when to use the highly efficient silent mode and when it needs to escalate to the verbose text mode?
Oh, right. Because if it just defaults to being silent all the time to save energy, it is going to fail miserably on the complex logic hurdles.
Precisely. To solve the switching mechanism, they implement a reinforcement learning algorithm called ARGRPO. Think of it as a highly calibrated reward and penalty system during training.
Okay.
The algorithm gives the AI a positive reward signal for using the efficient latent mode, saving those precious tokens, but only if the overall task is completely successful.
Makes sense. But how does the penalty physically work if it fails? Like, how does the math adjust?
When the AI attempts to use latent mode on a really complex problem and fails the task, the reinforcement learning algorithm backpropagates a negative reward. Physically, this adjusts the model's internal weights to decrease the probability of generating the LAT token in similar future scenarios.
Ah, and simultaneously increases the probability of generating the think token.
Yes. It carefully balances the incentives, teaching the model that while efficiency is good, accuracy is paramount. It learns to escalate to explicit text whenever its internal silent computation isn't robust enough to secure a win.
I have to play the skeptic here for a moment, though.
Go for it.
If the AI is thinking silently in this continuous, unreadable mathematical space, how do the researchers actually know it is reasoning? How do we know it isn't just skipping the thinking phase entirely, treating the four tokens as filler, and just blindly guessing to get to the action?
That's a great question.
Hmm?
The researchers anticipated that exact skepticism, and they specifically tested for it. You recall we mentioned the latent block is exactly 4 tokens long?
Right.
Those represent 4 iterative steps of internal computation. During those steps, the data passes through a projector network.
Wait, a projector network, what is that actually doing in this context? Is it translating the numbers or is it doing something else?
Think of a projector network as a refining loop. It takes the multidimensional mathematical representation of the problem and cycles it, transforming and refining the vector space step by step.
Okay.
It's like churning butter. Each pass through the network condenses and clarifies the information before the final action is chosen. To prove this was happening, the researchers ran an ablation study.
An ablation study where you systematically strip parts of the architecture away to see what breaks, isolating the variables.
Exactly. They reduced the latent block from 4 refining steps down to just 1 step.
And what happened?
When they did this, the model's accuracy on downstream tasks dropped significantly. When they restored it to 4 steps, performance rebounded.
Oh, wow. So that proves the thinking is real and necessary.
Yes. Those 4 steps are not hollow filler. The model is genuinely using that sequential computational space to process the state of the environment, weigh options, and formulate its next move. It's performing tangible cognitive work.
Okay, the theory is airtight, and the architecture is clearly brilliant. But let's look at the actual data. Does this framework survive contact with real-world benchmarks? Because the token savings reported in this paper are just staggering.
They tested ALR extensively across 2 main domains, agentic search and tool use. In agentic search, they apply the framework to Qwen 2.5 models at both the 3 billion and 7 billion parameter scales.
To give you context, listener, 3B and 7B are relatively small, highly efficient models. They are designed to be fast, but they usually struggle with complex multi-step reasoning compared to massive models like GPT-4.
Yet, when equipped with ALOR, these smaller models reduce the number of generated tokens by up to 43.6% during web searches.
They essentially cut the computational cost in half.
Exactly, while maintaining or slightly improving their exact match accuracy compared to the baseline. But the tool use domain is where the numbers completely redefine the landscape.
Right. They tested a model called Qwen 3.4b thinking, which is natively designed to interact with external software tools. Using ALR, they reduced the total tokens generated by 84.6%.
An 84.6% reduction in necessary compute.
Think about that in human productivity terms. That is the equivalent of cutting a standard 8-hour workday down to just over an hour, and somehow delivering a significantly better presentation at the end of it.
It's unbelievable.
Because the average accuracy didn't just hold steady, it improved from 86.1 to 89.2. How does an AI using 84% less effort actually become objectively smarter?
It circles back to the context window degradation we discussed earlier. When an AI is generating thousands of words of self-narration across multiple turns, the context window gets bloated with noise.
Right, all that text piling up.
The model's attention mechanism gets spread too thin. It can literally lose track of the original goal amidst its own verbose ramblings. By stripping away all that textual noise and using clean, highly condensed latent vectors for routine actions, the AI maintains a hyper-focused context window. Less noise equals better execution.
That makes total sense. And the behavioral analysis they conducted, looking specifically at when the AI chose to use text versus latent space, really solidifies our System 1 and System 2 analogy.
The behavioral patterns were incredibly consistent. Turn 1, the very first step where the AI receives your initial prompt and has to formulate a broad strategic plan, utilize explicit text reasoning the most heavily. The AI takes a moment to narrow its strategy and break the problem down.
But the later turns, which are primarily routine data gathering, like reading a search results snippet, deciding to click the next link, scrolling down relied almost exclusively on the silent latent mode.
Yeah. They also tested the framework across vastly different difficulty levels. They used datasets like Bamboogle and 2Wiki.
Those are notoriously difficult multi-hop reasoning benchmarks. They are designed specifically to trip up language models by requiring them to synthesize obscure facts from completely different sources.
Exactly. And on those brutal datasets, the AI recognized the complexity and triggered way more explicit thinking. Its latent fraction, the percentage of time it stayed silent, dropped down to 59% and 75%. It knew the task required deep deliberation, so it leaned heavily on text.
But on the easier data sets, like Trivia QA, which mostly requires simple, single-step factual retrieval, it operated almost entirely in silent latent mode up to 91% of the time.
It just breezed through the trivia using its computational muscle memory. It is exactly what you want an intelligent autonomous agent to do. Scale its processing effort directly to the difficulty of the problem.
So we have to ask, what does this actually mean for the trajectory of artificial intelligence? Let's bring this right back to you, the listener.
Yeah.
Why does understanding this highly technical paper give you an edge? It matters because this is the blueprint for the very near future of the AI tools you use every day.
Without a doubt.
If you are a developer integrating AI into an app, a business owner automating workflows, or just a heavy power user, you are currently paying either in subscription fees, direct API costs, or just sheer waiting time for hundreds of wasted tokens every single time you ask an AI to do something complex.
AIR fundamentally alters the economics of agentic AI.
It means vastly faster response times. It means API costs will plummet because you aren't paying for a machine to write an essay to itself before it clicks a calendar invite. And it means we get genuinely smarter digital assistants that smoothly adapt their computational horsepower to the actual difficulty of your prompt rather than using a sledgehammer to crack a peanut.
But there is a deeper, almost philosophical shift happening here as well. A shift that leaves us with a rather profound question to consider.
What's that?
If AI is now successfully learning to bypass human text, if it is learning to think far more efficiently in its own continuous multidimensional mathematical space, how long until its most complex, groundbreaking problem-solving happens entirely outside the bounds of human language?
Oh, wow. That is a staggering implication.
Right. When that happens, when the AI is reasoning in vectors and dimensions we physically cannot read or comprehend, will we even be capable of translating its best, most innovative ideas back into words we can understand?
That is a lingering thought right there. We started out talking about that brilliant friend who over-explains everything, who just talks way too much. But maybe the real paradigm shift isn't just getting them to summarize.
Maybe not.
Maybe the future of AI is the silent genius, the entity that quietly crunches the complexities of the universe in a mathematical language entirely its own, and simply hands you the correct result. Keep questioning, keep exploring, and we will catch you on the next deep dive.